Hello viewers, you are watching Chem Simplified. Today we will discuss how to calculate the overpotential and Tafel slope of oxygen ablation reaction. First of all, we will discuss some important points regarding oxygen ablation reaction. It is the anodic half reaction during the water electrolysis and mostly metal air batteries, and it is a very sluggish reaction because it involves 4 electron transfer and normally very high energy is required to drive this reaction. The 1.23 volt is the potential, the thermodynamic potential that is required to drive this oxygen ablation reaction under the standard condition. What is the overpotential? Overpotential is basically the potential at the current density of 10 milliampere that is required beyond this thermodynamic potential of 1.23 volt to derive the oxygen ablation reaction. We measure this by subtracting 1.23 volt from our measured potential at the current density of 10 milliampere. Uh, and then what are the sources of this overpotential? Due to the slow charge transfer kinetics, there is activation overpotential, ohmic losses like due to the resistance in cell and electrolyte and electrolyte interface, and the mass transport limitations that are especially due to the oxygen buildup in experiment. The onset potential is the potential or lowest electrode potential at which the noticeable current begins to flow during an electrocatalytic reaction like in oxygen ablation reaction or HER, and it marks the beginning of the chemical catalytic activity of the material. The overpotential is the extra voltage that is required to apply beyond the thermodynamic potential of 1.23 volt to drive the reaction, and it quantifies the energy efficiency of a reaction. Some important point that must be remembered before going for the experiments. For OER reaction, we have to measure LSV or linear sweep voltammetry in applied potential window of 0 to 1 volt when we are using silver chloride as a reference electrode. Then you have to convert this potential of silver against the silver chloride to the reference hydrogen electrode RHE by using the formula, and then plot the graph of current density against the potential versus RHE, and read the potential at the current density of 10 milliampere and subtract 1.23 from volt to it to get the over. Here I have collected the data for my two electrodes, that is bare F2 and my catalyst that is deposited on the FTO. I already copied this data to the origin. So first of all, we convert this data to potential to the RHE, current to the milliampere. So in column A, I have potential. So I will write A plus in bracket 0.059 multiply, and the pH that we have of our electrolyte was 13.29 that we have measured during our experiments, and then plus 0.1975. Similarly, in column B, we have currents in amperes. So we have to convert into milliamperes. So I will write B multiplied by 1000. Same process will be repeated on C. Now I will make sure that the axes are XY and XY. Then select all the columns and plot a graph. But in our case of our material that I have mentioned AS deposited on FTO, it shows a very good catalytic activity and it shows a current density of around 450 milliampere per centimeter square. And now I will read the current at potential at the current density of 10 milliampere. I place the cursor here 10.5, so we'll take it. It is 1.45 volt. So I will write here the over potential at current density of 10 milliampere would be 1.45 minus we have subtract 1 we have to subtract 1.23 volt, and it would come out to be approximately 0.22, and if I multiply it by 1000 to convert into millivolt, it would be 220 millivolt. 220 millivolt is kind of a good overpotential. Normally, the overpotential values between less than 300 are considered as a good for the sake of oxygen evaluation or oxygen evaluation in water splitting. And a very good material must have value less than 200. I have seen a few papers that have reported the value of 190 and even lower than 190 millivolt. So try to achieve the as lowest as possible. So this is the overpotential that we have measured at the current density of 10 milliampere, that is 220 millivolt. Before going into the calculation of Tafel slope, first we will discuss few things. Here is the Tafel equation. Eta represents the overpotential, A represents the intercept of the graph of overpotential versus log of current, B is the slope of the linear fit of the graph between overpotential and the log of current, and J represents the current density here. And then what is the significance of Tafel slope? Tafel slope normally indicates the reaction kinetics and possibly the possible rate determining step of the reaction, and the lower Tafel slope means the faster reaction kinetics. Here I have added few typical slope values. Tafel slope value of 30 to 40 millivolt per decade suggests the faster reaction kinetics, while 60 to 120 millivolt is just one electron transfer rate determining step and some sluggish reaction kinetics. And one important point that must be remembered: use the linear region of overpotential versus log of current density plot for the accurate fitting of the Tafel slope. Now we will move towards our actual data to calculate the Tafel slope. So here we will locate the point at the current of 10 milliampere. Here at the first point in bare FTO case, I will copy all the data from this point to the end, to C, and I will add the next sheet. Place this data in second column, and then cut the current column and paste it in first column. Okay, and similarly we will copy the data for our second catalyst, that here 10.21, and I will copy this to the end C and paste here in this column, and then copy the current and paste it here. Now we have to take the log of the current. Simply I will write log column A, and then the log of column C. We have to subtract 1.23 from this value, B minus 1.23 and T minus 1.23. Now I will take first 20 points from this and plot as a scatter plot, two lines of pairs. Then I will apply analysis, fitting, linear fit. I will show open dialog, add all plots in active page. Okay, we have a slope value of FTO to 0.20162, and then multiply it by 1000. It will be 201.62 millivolt per deck. Tafel slope of AS/FTO, and it comes out to be 0.089.95, and I will multiply it with 1000, and it will be 89.95 millivolt per deck. This lower Tafel slope value for AS deposited on FTO shows that this reaction material has show faster reaction kinetics as compared to the bare FTO, which supports our good electrocatalytic activity for OER of this material. Possible reaction mechanism is four-step mechanism. In first step, hydroxide ion from the uh, electrolyte adsorbed on the surface of the uh, metal catalyst. Second step, metal hydroxide and combine takes the proton from this and convert into metal oxygen and release along with the release of water and one electron. And then the third step again the formation of metal hydroperoxide, and then in the last step the evolution of oxygen. uh, as we have calculated the slope around 90 millivolt per deck, and the slope value that between around 90 to 100 millivolt per deck often correspond that the second step being the rate limiting step. So in our reaction this step would be the rate determining step. This step involves electron transfer and possibly a proton coupled electron transfer, means a proton is also being transferred in this step. And the rearrangement of surface bound hydroxide species means hydroxide species are converted into MO. So this would be the possible reaction mechanism of our experiment. So this is all for today's video. For more interesting and videos regarding electrochemistry, keep watching Chem Simplified. Thank you.